Integration by substitution is actually something we learn in Calculus 1, but I think it's really important to do a good review of it here at the start of Calculus 2 because it's really important. Our first two chapters are very, very heavy in integration, especially our second chapter. It's all about advanced integration techniques. And at the end of Calculus 1, integration by substitution is one of the trickiest things we do. And here in Calculus 2, integration by substitution is going to end up being one of the easiest things we do. So I like to start with a good review of integration by substitution, get everybody kind of back up to speed and back used to doing math with something familiar, hopefully. Get them back just in the mindset of doing math, hopefully with something familiar, something comfortable. And this is also going to give you a chance to review some other integration rules along the way. We're also going to have to do power rule and some rules with trig functions, things like that. So always start Calculus 2 with a review of integration by substitution. So when we learn how to do derivatives back towards the beginning of calculus, we learn three more advanced special rules for derivatives. And I'm actually going to call these special derivative rules. And these are things that we need to look out for that tell us that we can't just apply our basic rules term by term, that we actually need to apply a special formula. So if you're asked to take a derivative and you see a product of two functions of x or a quotient of two functions of x, then we have a special product rule and a special quotient rule that we have to use. We also have a third rule called the chain rule, and the chain rule is for when we see composite functions. And composite functions we learn about in algebra class. That is when we have one function plugged into another function. So kind of in easier terms, there's like an inside function and an outside function. So with derivatives, we have to remember all three of these rules. So the nice thing about antiderivatives or integration is that all three of these get bundled into one rule. So we don't have to remember three special integration rules. There's only one special integration rule right now, and that is integration by substitution. Now we're going to learn a lot more integration techniques throughout Calculus 2, but just as a review from Calculus 1, and what we need to move forward from here is this integration using substitution. So this integration by substitution will take care of products and quotients and composites. And integration by substitution is also sometimes called U-substitution. And really, integration by substitution is just based on the derivative chain rule. When you do the chain rule, that formula sometimes just naturally creates a product or a quotient, depending on what those functions look like. So if we were asked to take the derivative of f of g of x, that is a composite function because the g function is plugged into the f function. They're not multiplied. One is actually plugged into the other. So it's a composite function, and to take this derivative, we would have to do the chain rule. So we would start with the derivative of the outside function, and you'd leave the inside alone. and then we would multiply by the derivative of the inside function. So by doing a chain rule, it just kind of naturally creates a product. So we still see this composite. And now we also see this product, but depending on what kind of function g is and what happens when we take its derivative, it's possible this could also be a quotient. Products and quotients are really the same thing. Multiplying is the same as dividing by the reciprocal, or dividing is the same as multiplying by the reciprocal. So that chain rule could create a product or a quotient. So derivatives and antiderivatives are opposite operations. So when we're asked to take the derivative of f of g of x, we get this function. And if we were to do this backwards, the process would be called the antiderivative. So if we were asked to take the antiderivative for f prime of g of x times g prime of x dx. Now that dx means that somebody else has already taken the derivative with respect to x, and we're being asked to undo the derivative. Go back to what the original function was before the derivative was taken. And they're just letting us know to consider x to be the variable. They're letting us know x is the variable here. Now, this semester, we're only going to be dealing with functions of one variable, but it's possible next semester in Calculus 3 that we could see problems that have functions with more than one variable. And then that dx would be really important because we would have to pay close attention to that to see what variable we need to consider to be the variable in our problem that we're doing our antiderivative rules on. So even though we just went through the chain rule a minute ago, we know what this is going to turn into because the opposite of derivative is antiderivative. So it should take us back to f of g of x. But if we didn't know that, we would look at this and say, oh man, I've got a composite function right here, and I've got a product of two functions of x. Both of those two situations require special rules when it comes to derivatives, which means it's also going to require a special rule when it comes to antiderivatives. So usually the first thing you need to check, and sometimes the most difficult thing for people, is to just decide when they're supposed to do integration by substitution. So if your integrand, and the integrand is the function that we are integrating here. So this is our integrand. If your integrand contains a product, quotient, or composite, and you can't fix it with just some basic algebra, then you're going to have to use integration by substitution in order to find the antiderivative. So that's really our first hurdle, is to decide when do we need to use integration by substitution. So if we see products, quotients, or composites for derivatives, we know we've got special rules for derivatives, 3 separate special rules. If we see products, quotients, or composites with antiderivatives, all of them get combined into one special rule, and that's going to be our integration by substitution. So our goal here is to make it so that we don't see a product, a quotient, or a composite. And we're going to start with the most complicated piece that we're going to see in this integral. Now, you're not always necessarily going to see the product or the quotient, but you should always see a composite function. So that's something important that you should realize right away. A lot of people will look at these problems and say, well, I don't see a product or I don't see a quotient, so maybe I don't need to use U substitution. And that's not always going to be the case. Just because the format for our chain rule looks like a product doesn't mean that G prime isn't going to turn out to be just a times 1 or times some other real number coefficient that we don't recognize as a function of x. So the product or quotient may not always be there, but we will always see a composite. And that composite function, if you look at our options, is definitely the much more difficult piece to deal with in that integrand. And that's where we want to start. So we're going to do some substituting. And in the process of this substituting, we're going to change over this integral to be starting off from in terms of x, and we're going to change it to be in terms of u. So that's why I said sometimes this is called u substitution. So I'm going to write my integral again. And this could look lots of different ways. But once you've decided that you're going to do u substitution, you want to identify where the composite function is. There should always be a composite function in your integrand. Now, one of those functions individually is fine, but the two of them together is not fine. So we need to get rid of one of them, and it's going to be easier to get rid of the inside piece. So we're going to let u equal the inside of your composite function. We're going to let u equal g of x, which is the inside of the composite function. So typically g of x is going to be some entire function of x on its own that's going to have its own antiderivative rules that we have to follow. But then f prime here is also some function of x, and it could be some completely different function of x that has its own separate antiderivative rules that we would have to follow. And we can't make the decision of which one to do first, which one to do second, which one's more important. And if there's not any algebra we can do to simplify that, to kind of combine them, we don't have the authority to decide who's more important, who goes first. So the easiest thing to do is to just get rid of g of x. Get rid of it completely. And what we're doing here is we're replacing g of x with just a single linear variable. Just like an x, except we're calling it u. So if there's just a single linear variable in there, it's just like a placeholder, that inside function's completely gone, and all we have to deal with there is how to do the antiderivative of the f prime function. So that's our first step, is figuring out what we're going to let u be equal to, finding your composite function and letting u be the inside of it. So we are starting our process of changing this integral to go from being in terms of x to being in terms of u. Now remember, I said earlier, this dx at the end means that we're treating x as the variable. But with this u substitution process, we're trying to get all those x's replaced with u's, which means we're going to have to get the dx replaced with a du. So in step number 3, what we want to do is we want to take the derivative of both sides of that u equation. And that will give us a relationship between du and dx so that we can do a replacement for dx. So we know we're going to replace g of x with u, and in step number 3, we're going to be able to find a replacement for the dx, and as long as we've done everything correctly, then g prime here at the end should take care of itself. And we should be left with something when we do those replacements that we can apply some of our basic antiderivative rules to, like a basic power rule or a basic trigonometric rule or a basic exponential rule. We shouldn't have to do any sort of tricky antiderivatives at this point once we get this in terms of u in order to do the antiderivatives. So we should be able to substitute. And integrate. But your last step is always going to be to write your answer back in terms of x. Because this problem started off with x's in it, these u's were just a tool for us to be able to solve the problem. They're completely arbitrary. If the problem starts with x's in it, we need it to end with x's in it. So once you're able to use your integration rules, then we need to write the answer in terms of x. So we actually need to write out this work that we're doing here in step number 2 and step number 3 so that when we have our answer in terms of u there in step number 5, we can easily go back and see what we need to replace the u's with to get our final answer. All right, so let's actually look at a couple of examples really quick. And the instructions are just to integrate. And the first one that we want to try, we'll keep it pretty simple here to start with. It's going to be (5x) times the square root of 1 minus x squared dx. 5x times the square root of 1 minus x squared dx. So our very first challenge is to be able to look at a problem like this and recognize that we have to do u substitution to get the answer. We can't distribute the 5x into the square root. There isn't any sort of rationalizing we can do to get rid of the square root. It's not an equation. we need to find the antiderivative of this function, 5x times the square root of 1 minus x squared. Now that function contains a product because it's 5x times square root of 1 minus 2x, or excuse me, square root of 1 minus x squared. So we can split this into a product of two functions. So we definitely see a product. Now one of those should be a composite function, which means one of them has an inside and an outside. So our next step is to try to figure out which one is the composite. A lot of times the composite will be able to easily be identified because you'll see parentheses and a function inside and an operation outside. Now this one doesn't have parentheses besides the blue ones that I just drew, but there is a math symbol that kind of encloses a function, and we can use that to help us identify an inside and an outside. The square root of 1 minus x squared is our composite function. The 1 minus x squared is the inside, and the square root is the outside operation. Now, integrating a square root is not a problem. We really could just do the power rule for that if we wrote the square root as a 1/2 power. The problem is that the inside of the square root is not just a nice, simple, single linear x. The inside is some entire crazy function of x. So we want to replace the inside of the composite with u. So we're going to say u equals 1 minus x squared, the inside of our composite function. And then we need to find a replacement for dx, because this is the first step on our way to rewriting this integral in terms of u. So I'm going to take the derivative of both sides of this equation. So the derivative of u in terms of u is just a 1, and we write du, and that means I took the derivatives of the u's. I considered u to be the variable. So on the left-hand side, I'm considering u to be the variable, and the derivative of u is 1 with respect to u. On the right-hand side, the derivative of 1 is 0, and then I've got minus the derivative of x squared is 2x. And that's what I get when I consider x to be the variable on the right-hand side, so I say dx. And we're looking for a replacement for dx. So sometimes the easiest thing to do here is to solve this equation for dx. So just whatever ends up there on the right with your dx, just divide it over. And then we'll know what to replace the dx with in that integral. So negative 1 over 2x du can be plugged in for the dx. So there's two things that we are going to plug in and try to rewrite this integral. I'm going to replace 1 minus x squared with u, and I'm going to replace dx with negative 1 over 2x du. Now we have not said what we're going to do with the 5x, so we just leave that alone for now. So I've got 5x times the square root of u, and then for dx, I'm going to do negative 1 over 2x du. And if we've done this correctly, if there was any sort of if there was any sort of product or quotient, the x's in the product or quotient function should cancel away, which they do here. I've got an x out in the front that's being multiplied, and then when I pulled in my du, I had an x there that's being divided, and those will cancel each other out. So if I clean this up a little bit, I've really got negative 5/2 times the square root of u du. And we could easily integrate that because now the only thing that has a variable is square root u. And we could write our square root as a 1/2 power and just do a power rule on it. So remember from Calculus 1, when we do the power rule, for antiderivatives, we add to the exponent. So that's going to be u to the 3/2. And then whatever that new exponent is, we flip it out front. And also, the coefficient just gets carried along. And because we're not evaluating, this is an indefinite integral, we don't have numbers to plug in, we also are going to have a plus c on our answer. That is not our final answer though. That u was completely arbitrary. That was just kind of a tool that we used to help us integrate. We have to write this back in terms of x. So I'm going to go ahead and multiply those coefficients together and simplify them a little. And it looks like we're going to get -5/3. And instead of u to the 3/2, remember I wrote it out up here. I said u was 1 minus x squared. This is really just going to be 1 minus x squared to the 3/2 plus c. That is our antiderivative. And we got it by doing u substitution.